How do you solve a problem? Just like we put T over here, the force of gravity. So if you have a planet going around the sun, obviously if it's moving in it has an acceleration, unbalanced force. The only force on it, there's no strain, there's no nothing. What's on it? Gravity. So the sum of the forces is gravity equals mass times the acceleration of the planet. And we have the force of gravity between the sun of mass m and, let's say, s, and mass of the earth, me, over r squared, where r is what? R is the distance between the sun and the earth. The orbit, okay, so r sun earth, let's say. That's the force between the two. And that unbalanced force gives rise to an acceleration. And the relationship between the force and the acceleration, the cause and the effect, is the force is equal to the mass times the acceleration. Now, which mass? What was that? Is this the mass of what? What are the possibilities here? The mass of the sun or the mass of the earth? Why the earth? Why not the sun?
It's greater.
So why isn't the sun moving if there's an interaction between the two? We're just talking about the force between the two. We didn't say the force of the sun on the earth, which is the force between the two. The answer is that the sun does move as a result of the earth's gravity, but obviously much, much less because we're much less massive. Okay, so there's a combined motion and it moves around the combined center of mass. But if we're talking about the motion of the earth, then this is the force, and we're talking about the mass of the earth and the acceleration of the earth. If we're talking about the motion of the sun, the force is the same, okay? The motion of the sun around the earth, so to speak, but here would be the mass of the sun and acceleration of the sun. Okay? We're saying that the force of gravity is g mass of sun, mass of earth over r squared, and that's equal to mass of earth, acceleration of the earth, mass of sun, acceleration of the sun. It's the same force between them. Now, you don't see the sun going around the earth, obviously, but that's what it would be. How could this equal this? Now, how could it be that the same one is equal to, how could it be? How could it be that this is equal to, let's say, mass of the earth times acceleration of the earth also? Is that possible?
Well, because it has the mass in there, so if the mass of the earth is smaller.
Right. This is tiny, and this is huge. And this is tiny, and this is huge. Okay? So it would be something like that. But of course, the bottom line is that it doesn't, it's not that the earth goes around the sun and at the same time the sun goes around the earth. There's a combined motion. A gravitational source, a star, a planet, an object, doesn't matter what it is, and another object here. And we discussed this actually, we spoke about it. If I just let this go, this one should move to this and this one should move to that. If this one is much, much more massive, the acceleration as a result, there's the same force between the two, given by this. That's the force between this one and that one. It doesn't matter which one you're talking about, it's the force between them, pulling them towards each other. The acceleration of this one as a result of the force will be given by that force divided by its mass. If its mass is very big, it'll be a very small acceleration. The acceleration of this one will be the same force divided by its mass, but if its mass is very small, it will be a big acceleration. So the two of them experience the same force, but will move differently because they have different masses. The bigger mass experiencing the same force will move with a smaller acceleration. The smaller mass experiencing that same interaction force will move with a bigger acceleration. They're moving towards each other slightly. Usually, we're dealing with objects which are so different in mass that we ignore the motion of the bigger one. Okay, so we'll say this one will fall into that one. Really, they're falling towards each other. Okay, if it's the Earth, there's so many things on all different sides, they all cancel out, so basically the Earth is not moving. We have an object of mass m over here near the Earth. Okay, it and the Earth are attracting each other by gravity. and I want to find out what is its acceleration. What is the acceleration of this object, this piece of chalk? Okay, with the mass chalk. All right, what is its acceleration due to the interaction between it and the Earth? How would you solve that? Okay, what's the formula? The acceleration of the chalk equals the sum of the forces on the chalk divided by the mass of the chalk. Right? Agree? A is equal to F over M. Okay, what are the forces on the chalk that we're talking about? It's falling. Gravity. Neglecting air resistance and all that kind of stuff. What is it equal to? G, mass of the chalk, mass of the Earth, over r squared. Now r squared, what we do is we take not the distance between the chalk and the Earth, which is 0. Let's say here's the table, or the ground floor, or we know which floor do we take. The answer is we take the center of the Earth, and maybe at some point we'll learn why. But basically, the gravity acts as though everything were combined at the center. Okay, otherwise we would get the observed result if it's lying on the surface of the Earth that there's no gravity because the distance is 0. And then you have to determine where is the surface of the Earth, on the ground floor, on the 6th floor, in the basement, on the mountain, right? The answer is that it's the center of the Earth is what's the relevant distance. So it's the distance between the center of the Earth and the chalk, basically the radius of the Earth, divided by mass of the chalk. What magnificent result do you get? What is this equal to? Read it out to me. G M-E.
Over r squared.
What disappeared?
MC.
Mass of the chalk.
So what do we find? That the acceleration due to the gravitational interaction of the chalk and Earth is not dependent on the mass of the chalk. Now what happens if I took this book instead and dropped it? What do I have to change here?
It doesn't change.
Doesn't matter what the mass is. The acceleration due to gravity is independent of the mass. Okay. It's a beautiful, beautiful result. You have an equation, two equations, unrelated. One is F is equal to ma. The other one is the force of gravity is G-M-M over r squared. Because both of them have m in there, they cancel out. Now what have I assumed here that I really shouldn't assume? It's something subtle, and I think we discussed it in the beginning. What is the m in F equal ma? Remember we spoke about at the beginning, it's inertial mass. It's inertia. It's the resistance to motion. By definition, A is equal to F over m. It's the amount which you have to divide the force by to get the acceleration. It's the resistance to motion mass. This mass is something entirely different. This is the gravitational mass. This is like the force of gravity between things. It's not the same mass. It's a different mass. Okay? Gravity is like you have electric charges and they interact with each other. Gravity is like a charge and it interacts. It has nothing necessarily to do with the resistance to motion, and we discussed this at length in one of the earlier classes. Okay? So really, I should have this force over here where I have B or C. This is gravitational, and this is inertial. This is mass inertial, and this is mass gravitational. So really, my formula should have mass of the book gravitational divided by mass of the book inertial over here. So this multiplied by that. Do you see that? Do you see why? Because I can't really cancel them out because they're different things. But I'm separating them out. I'm taking the gravitational mass that governs the interaction here, the attraction, and the interaction and the inertial mass here, which comes from A is equal to F over m, the resistance to motion, and pulling it here. So really I should have this times that. What I can do is I do experiments, and I drop two things of different masses, and I find that they have the same acceleration. And that tells me that these are equal, that this is 1. Okay, I find that it doesn't depend on this. I find that they all have this acceleration, the same acceleration, just governed by the mass of the Earth and the radius of the Earth, G. which then tells me that this has canceled out. Which then tells me that the gravitational mass is equal to the inertial mass. Two seemingly unrelated basic entities in nature are identical, which means probably they're the same thing. And the fact that inertial mass, the resistance to motion, is the same thing as, not only equal, but it's probably the same as gravitational mass, means that gravitation is something very, very fundamental and basic about matter. The gravitational interaction, you would be extremely surprised if I told you that the mass of a charge is equal to its charge. Why should the mass of an electrical charge be equal to the amount of electrical charge it has? Why should they be related? But they're not. Why should the gravitational charge, the m that appears in this formula, be the same as the inertial mass, as resistance to motion? Turns out it is, and that tells you something very fundamental about the nature of space-time, the nature of mass and the relationship, and it led pretty much to the development of the general theory of relativity.
I'm a little bit confused. How do you get the mass? How do you get the magnitude of the mass? How do you get the mass, number of mass, without using the gravity and power?
Okay, remember that mass has nothing to do with gravity, right, necessarily. At least naively we would think, in space where there's no gravity and nothing, things have mass. If you pushed on it, it would be harder to push on an elephant than on a ping pong ball. We discussed that, right? So obviously the elephant has more resistance to motion than the ping pong ball does. Or two ping pong balls have twice as much resistance to motion as one, right? Why? It's not gravity. There's no gravity.
Okay, that's not gravity. Now how do you get the mass is bigger?
So that we call that mass. That quality which it has such that it's difficult to move it, we call that inertial mass.
So how can you find the inertial mass?
How would you
Yeah.
measure it, you mean?
Yeah, how can you measure?
Okay, we would have to set up an experiment where we're pushing on it and it's resisting our motion and there's no other forces around, and we see how much it's resisting our motion. For example, if we put it on ice skates and there's no friction with the earth, or we put it in water where there's no weight, it's like buoyant, it's just hanging there, kind of like weightless, so to speak, and we see how hard it is to push. Of course, you're pushing against the water. Also, if you factor out the water push, and you see just the net resistance to motion, or you go out into outer space, far from any planet. What were the assumptions that went in here? Again, I'm repeating from the previous lecture. One of them was this thing. Okay, then we had just this this number here to scale it correctly. When we cancel this, what were we assuming? We're assuming that these are the same masses. Why might these not be the same masses? All right, we had two separate equations. One is the equation we had the equation F equals ma. Now we had the equation F is equal to this. Is that the same thing? Are they the same F's? Are these the same F's? F equal ma and Fm1 equal Gme m1 over r squared. Okay, why?
If the acceleration is gm over r times the mass, it would be the first one.
Okay, how do you know? What are you saying? Why can we put one into the other? You said that the acceleration is gm. Well, getting that the acceleration is gm over that was when we assumed that the two f's are the same and we equated one to the other, right? We said f equal ma, and then we said f is equal to gmm. So then we made gmm is equal to ma.
Because we said that a equals to gm over r squared, so and that's a times
Okay,
m.
right, but this step comes after. In other words, the first step was this: f is equal to ma. That's what we learned in the first chapter, where it was f is equal to ma. Then we did that force of gravity is equal to this. All right? Then what we did is we said, well, if this, we said this is equal to that. MA equals this. Therefore, A equals this over M, right? This is basically this equation, right? A equals F over M, right? This is A is equal to F over M. We took that equation, we stuck in, for F, we stuck in this thing on the top here, and divided by M. That's how we got this, right? But who said that this F is the F that goes on top here? Is that the same F? What about if I did, wait, how about if I wrote this? Wm1 is equal to this. So it suddenly becomes, just by changing the terminology, it suddenly, you said, well, A is equal to F over M, not A is equal to W over M. This is W, all right? If I just said that, I said, well, A is equal to F over M, and W is equal to this, the weight. Therefore, A is equal to this over this. Say, no, what'd you do? Right? A is equal to F over M, and this is W. You put W on the top here. Right?
Oh,
Not, it's supposed to be F, not W. So why did I just changed it. I called it F, and then you said, okay, now I've called it F, so I can put it in. Why? All right, so the W is not, maybe not appropriate here. This equation says, the greater the force, the greater the acceleration. The greater the mass, the less the acceleration.
Yeah.
Right? This equation makes sense, we accept it. Okay, this equation makes sense. There are some things that we didn't explain exactly, right? We'll get to that maybe eventually, why it's r squared, seeing how the g comes in. But we know why it should be 1 times the other, not 1 plus the other or minus the other, and so on. We understand why the n's should both be there. We understand why they should both be on top. We understand why the r should be there and why it should be on the bottom. But who said that this f belongs here when we're talking about the acceleration? Okay, the answer is this is a general equation for any kind of force on a mass. You have an unbalanced force on a mass, it gives rise to an acceleration. That's a general principle of nature in our universe, okay? Where this relation, in specific relation holds. A is equal to F over M, not F squared over M cubed or all kinds of crazy things, okay? A is equal to F over M. Any force, unbalanced force, net force, whatever, acting on an object of mass M gives rise to this acceleration. The acceleration of the mass M1. We want to be more specific. The acceleration of the mass M1 is equal to the sum of the forces on M1 divided by M1. Okay? Any force, including the electrical force, tension in a rope, gravitational force, friction force, any force, net force. If they're all of those acting all together, you add them all up, get a vector sum, put it in here, divide by the mass, you get the acceleration. All right? So if this is a force, then you can put it in here. Is it a force? Well, yes. You measure the amount of force of gravity. We find the force of gravity has this equation. This equation has nothing to do with this equation. F equal ma has nothing to do with F is equal to gmm. This is the force of gravity on an object. Okay? Or the force of gravity between the Earth and an object 1. Okay, the force of gravity between the Earth and an object 1 is equal to this. Okay, again, the subscripts are useful, right? You get used to putting in the subscripts to make something very explicit. So this is a specific force. This is also a law of nature. It's also universal. It holds everywhere. And this is a law of nature that holds everywhere. They're two separate laws that have nothing really one to do with the other. This just tells you about the gravitational interaction between any two objects. Okay, this is not a law of nature. This is a specific implementation of the law of nature to the force of gravity between the Earth and the object M1. But obviously I can put any object here and any other object here. Or I can take any two particles within any one object. Okay? The attraction of this molecule of chalk to this molecule of chalk, or this proton of the molecule to this electron of that molecule is the mass of this proton times the mass of that electron divided by the distance squared between them. Any two entities in the universe, I can take the gravitational force between them. Of course, the gravitational force between this electron of chalk and this proton of chalk is way, way, way overcome by 1,000 trillion other gravitational forces and electric forces and so on. So it's totally useless. There's no purpose for me to figure out what that gravitational force is because it plays no role whatsoever, really. But there is that force, but there is also this other force, and that force, and that force. So it's not useful. But the gravitational force between the chalk and the Earth is a useful thing because all these little electrical forces between each other cancel out pretty much and hold it together, right? But the force between here and here is not canceled out. That affects its motion down. Okay, so this is a general law, and this is a general law that have nothing to do with each other. One talks about the acceleration of a mass as a result of unbalanced forces acting on it. This talks about the force between any two entities to the gravity. But you can combine them and you say, well, the force between two entities is a force, and therefore the acceleration that would result if you apply that force is given by this equation. So I can plug in this F, doesn't matter what I would call it, W, the weight, P, doesn't matter what I call it, it's a force. It's this thing. So I can stick it in, okay? So that justifies this equation, where I inserted F in there. But what about these M's? Is this M the same as this M? What is this M? How did we get to this M? It was the amount of resistance that an object has to a force that's exerted on it. Right? And we said even in space, far away from any kind of planetary or stellar influence, when there's no gravity whatsoever, there's just emptiness everywhere. If you push on something of very small mass and something of very great mass, you wouldn't find that you push on them equally and they both move the same amount. It'll still be harder to move the more massive object. It doesn't weigh anything. It weighs 0. Why does it weigh 0? Because there's no big M. Right? Let's say just the big M by itself. It has its own gravity, whatever, but there's nothing pulling it anywhere. It has no weight. But nevertheless, it has resistance to motion. That's M. This is M, inertial. Inertial mass, resistance to motion. This M is a gravitational mass, mg. It's the amount of gravitational charge that an object has. And this is the gravitational charge of the Earth. We say there's some property of a mass that it attracts every other mass. It has nothing to do with inertia. It has to do with a certain, just like magnetism attracts, you have electrical forces, you have all kinds of things, right? Nuclear forces, you have a gravitational force, which causes an interaction, an attraction between any two masses. It has nothing to do with inertia, nothing whatsoever. Inertia is resistance to motion. The connection is that, okay, we'll see the connection in a second. There's no connection between the two, it would seem. Gravitational charge, which we also call mass in English, and it's confusing because of that. This is gravitational charge, the amount of attraction between objects. This is inertial mass. So really we have M gravitational charge and M inertial on the bottom. So we cannot cancel that. So what should we get over here? Equals what? G, mass of the Earth, over r squared, times mass gravitational of 1, mass inertial of object 1. Do you all see that? We did this last time. All right? G me over r squared times mg over my. Now this, for every object, will be the same. The mass of the Earth remains constant. The distance from the center of the Earth is constant. We take objects of different mass, and we drop them. What do we find, lo and behold? That this number is the same for every mass. Right? This is little g. This is the acceleration. We drop two objects, they follow the same acceleration. They hit the ground at the same time. What does that tell us? Based on this equation? If this number, this acceleration due to gravity, always comes out to be 9.8 meters per second squared, what does that tell us?
Mass of the gravity and mass of inertia is almost the same.
Right. If this number is the same, that's to be expected. But this number times this number should not always give us the same number, depending on this ratio. Right? Sometimes for one object, let's say you have, if there's no relationship between these two, how come it always cancels out? If it cancels out, it means that they're exactly equal. So we do it for one object. We do it for mass 1, and we find it cancels out. Then we do it for something much bigger, and we find it cancels out. Then we do it for something much, much bigger, and we find it cancels out. In other words, the gravitational mass is always the same size as the inertial mass. Eventually we conclude that it's the same thing. mean, it doesn't make sense to attribute two properties to something, that every object has two properties, and those two properties are always exactly identical, but they're different. So how do you know they're different? If they're totally identical in every experiment that you do, what does it mean to say that they're different properties? In physics, we don't give credence to a claim for something that you can't prove. It doesn't mean that things you can't prove aren't true, but they're not part of physics. All right, so physics can't say there's a difference between mass, gravitational mass, and inertial mass if there's no way that you can prove that they're different. Every experiment that you do, they always cancel out. They're always exactly equal. It's like saying, on one side of me there's a ghost pulling this way, and the other side of me there's a ghost pulling that way, but the forces are always exactly equal, and they always cancel out, and in fact, there's no stresses in my body because on each electron or proton or piece of my body, there's a ghost, one pulling one way, there's a ghost pulling the other way in each particle, and they always exactly balance out, so I'm not being stretched or pressed, I don't feel like nothing. No, you can't disprove such a thing, but you certainly can't prove it if it's always balanced out. So we just say, okay, fine, you want to believe in that, it's fine, it's okay, but it's not part of physics because, proved. This always cancels out. So physics can't claim that there's a difference between the gravitational. It seems that there ought to be a difference because there are different things. One is the resistance to motion, and one is the gravitational charge, the amount that things pull to each other with gravity. You could almost imagine a universe where there's no gravitational interaction, but there's inertia, right? Things have a mass, and it's harder to move 10 pieces of chalk than it is to move one piece of chalk. But they don't have to have gravity, or conversely, they can have gravity, but maybe they don't have inertia. Two basic laws of Newtonian physics, the law of inertia and law of gravitation, two of the three. F is equal to ma. The force that's exerted on a particle of mass m results in an acceleration a, or the acceleration due to a force F when applied on a particle of mass m. It's a beautiful equation when you think about it. You can go to it in depth. It's the simplest possible relationship between these three quantities. It's actually magnificent. Unfortunately, it's taught in such a way that people hate it and think it's trivial. Okay. Now, this thing here is the inertial mass. It's the amount of resistance when you push on something, you exert a force on something. It'll accelerate. The resistance to that is the amount that diminishes. The amount of acceleration that will result from force F is diminished by the amount of resistance. Clearly, the larger the force, the more the acceleration. The larger the inertial mass, the smaller the acceleration. So this is inertial mass. Now, Newton's law of gravitation is you have some kind of constant. The force between two masses, mass big M and mass small m, separated by a distance r squared. The larger the masses, the more the force, the more the distance between them, the less the force. And some kind of constant. But this is a different mass than this. This is the gravitational mass. The attraction of two particles to each other has nothing to do with the amount of resistance to motion. It's a different quantity. It's the amount of whatever gravitational charge that they have. And they're attracted to each other by this gravitational charge according to this equation, which again is very beautiful and as simple as possible. And so on. The stunning and totally unexpected thing was that it turns out that these two masses are the same. In other words, the property of mass that it has, that it resists your motion, your attempts to move it, to accelerate it, turns out to be exactly the same as the property of mass, which causes two masses to attract each other. There should be no relationship between those two things. In the same way that you have two charges, they attract each other or repel each other. That has nothing to do with how much resistance to motion there is. Right? You have a law K Q over R squared in electromagnetic, right? Electrostatics. The Q has nothing to do with the mass. It's a totally different thing. This is basically a gravitational charge. It's a Q for gravitational force. Okay, now why am I not calibrating? One person has a bigger piece of chalk, one has a smaller piece of chalk, somebody's using a pencil.
All the same thing.
Why is it all the same thing?
Not really, they could have different numbers.
Okay, there's an air resistance, right? That's true. Why are we assuming that they're the same? Force of gravity. Why? The force of gravity is pulling it down, and therefore
It does not influence.
it does not influence what. So let's see if we can make a complete statement, complete sentence.
Acceleration.
The weight doesn't affect the
Yes.
Weight doesn't affect.
The mass.
Oh, it certainly does.
The mass does not
Right.
affect it.
The mass. Well, the weight is the force. Even the mass. The mass certainly affects the force which it pulls. Right? It's m times m over r squared. One mass times the other mass. Right? The force of gravity is equal to the mass of the Earth times the mass of the object over the square of the distance between the center of the Earth and the object, with times some factor g. Right? Certainly does enter there. So why are we neglecting it? Okay, we did this at the beginning of the semester. We did this in the previous lecture. Why do we neglect it? You have the force of gravity.
Because the mass of whatever we're dropping is the near the mass of the Earth.
No. If that's the case, what would happen in this equation? You have the force of gravity, which is weight. The weight of, let's say, object m1 is equal to the force of gravity on object m1 is equal to what? The mass of the Earth times the mass m1 over r squared, where r is the distance from the center of the Earth to the object. Okay? Times this constant factor g. If we neglected this mass, we would make it what, 0? What would be the weight? 0. Okay? The answer is extremely important. It's in the notes. Okay? When we want to find out the acceleration of the object of mass m1, what is it equal to? What's the acceleration of an object?
F/1.
Which f? The net force on it. If I take this and just drop it, what net force is there on it? Only gravity. What's the gravity force on this? That. G is the little g. Little g is the acceleration. Okay. What is the force on this? The gravitational force? This equation. That's the force. The force on mass m1 is this. Okay? Divided by, what is the acceleration of mass m1? It's the net force, which is only this, because there's no rope, there's no tension. Divided by what?
The mass.
Which mass?
The mass of the object.
Mass of the object itself, which is m1. What happens here? Cancels out, and what do you get? Just g mv over r squared. Whatever mass we would put in, the mass would cancel out. So this answer will be independent of the mass, which is why we call it little g. It's a number that doesn't change. We have this mass cancels out, okay? And therefore, we get a number here that's independent of the mass. Whatever mass we would put in, we would get the same number. We call that number little g. Okay, this is very, very, very important. All right? I can tell you for sure it's going to be on an exam somewhere, this whole business. What do we learn from this? That what? How would you formulate it in a complete sentence? How would you say this in a complete and a grammatically correct sentence? Pardon me? You can start with, let's say, the acceleration due to gravity, or the acceleration of an object due to gravity is independent of its mass. Something like that. Okay? If you wanted to explain why, you can say that although the mass figures in or is part of the computation or the determination of the gravitational force on it, the mass appears inversely in the equation for the acceleration, and therefore it cancels out. But, you know, just to be able to state it as a sentence.
Say at the beginning of it? If
the weight of an object depends proportionally on its mass,
Right.
but its acceleration due to gravity depends inversely on its mass. Okay? So we can say acceleration of an object due to gravity is equal to the gravitational force on it divided by its mass. And since the numerator, which is the gravitational force, depends proportionately on the mass, and the mass is also in the numerator, they cancel out. Whatever, something where you could say it in such a way that somebody who hears you knows that you understand what you're saying, right? Somebody who never learned it might not follow it. It's too complicated. It's too compressed into one sentence. But if you can say it like that, then somebody who hears you says, ah, okay, this person obviously learned it and understands it. And therefore, the acceleration due to gravity is independent of the mass. If you think about it, you can see that outside, let's say, the planet Earth, if you think of the mass of the planet and the distance from the center, right, you can define at any point what the acceleration will be. Right? The acceleration is simply g times the mass of the Earth divided by r squared, the distance from the center. And at any point in space near the Earth, you can define what will be the acceleration at that point. You cannot do that, for example, with an electric charge. With an electrical charge, the force will be k q1 q2 over r squared. The acceleration will be this over m. The acceleration is that over m. Whichever charges you use will have a different acceleration, because you can't cancel one out of it. You can't cancel the mass out. So gravity is unique in that all particles follow the same acceleration, which means that these two masses are the same. And as a result, you can define a gravitational acceleration field, which means that if you think about it, the gravitational acceleration is a property of the space around the Earth, or around whatever it is that's doing the traveling. It's not a property so much of the interaction of the particle that's falling towards the Earth with the Earth. Because whatever particle would be there would fall with the same acceleration. So if there's an acceleration field, if at every point in space we can define an acceleration, just gm, mass of the Earth over r squared, irrespective of which particle you put there, that's the acceleration that will be there. That means that that acceleration is, in a sense, a property of the space around the Earth. It's not a property of the particle, because whichever thing you put there will come with that acceleration. Okay? So that gives us a hint that gravity and this relationship, this unexpected relationship between inertial mass and gravitational mass, gives us a hint that gravity is somehow related to something very fundamental about mass, because inertia, the resistance to motion, is certainly something very fundamental to mass, and something that has to do with space. Okay? It's kind of, in space, there's a field that tells how anything put there will accelerate. Okay. What's the amount of force needed to accelerate a fast car? Estimate the net force needed to accelerate a 1,000-kilogram car at 1/2 g. 1/2 g simply means 1/2 the acceleration of gravity. Okay? Gravity is acting down, but if you want a car to accelerate in this direction with 1/2 the acceleration of the down force of gravity. Now, why do you measure acceleration in g's? Does anybody know? Why does it make sense to talk about a fast car in terms of g? I mean, one has nothing to do with the other, right? The car is being accelerated in this direction. The gravity is working in that direction. So why do we talk about g's? Maybe you've heard about fighter pilots and so on, and how many g's they've experienced, or a jet, and what's the maximum g that will be experienced by a pilot flying it at the maximum speed. Okay? When you're in a car and the car is accelerating, what do you feel? You feel the back of the seat pushing against you. Right? Your back is against the seat, and the seat is pushing against you. Right? You feel kind of pressed into the seat, and you feel the seat pushing against you. Can you kind of feel that in your imagination now? Right? The car is accelerating, or a bus or train or whatever it is, or if you're on a plane.
You feel like you're pressed.
Right, you feel like you're pressed back, or if you're on a plane when it's accelerating on the runway, right? You're kind of pushed back like this, right? And the seat is kind of pushing into you. All right? On an elevator, what happens? A fast elevator at the very beginning, you feel you're pressed down to the floor, and the floor is kind of pushing on you.
Yeah.
Okay? Because what's happening is you have inertia, you're standing still, the elevator starts to move, it moves underneath you and pushes against your feet, and then your feet are pushing against the rest of your body, pushing you up. So the top of your body is here, and the bottom of your body is starting to move up, so you kind of feel pressed. Your feet feel pressed, and then they press the rest of you. Your back is against the seat, it pushes against you and causes you to move. Okay? Now, that force on your back pushing you is really physiologically indistinguishable from the force of, let's say, the elevator pushing you up on your feet. And it's also physiologically indistinguishable from the force that you feel now of your chair pushing against you, right? You all just take a second to become aware of what your body feels like right now, right? Your bottom is on your seat, and you're kind of pressed down against it, and the chair is pushing up against you. Okay? If somebody were pushing on you or somebody sat on you right now, that would be even more intense, right? You'd be pressed down more into the seat, you'd feel that more. Okay? That's exactly the same feeling that you feel in an elevator, which is not gravity, it's a force pushing against you, accelerating you up, or a force pushing against you in a car, pushing you forward, causing you to move along with the car. All right? So, if you're in a jet and the jet is accelerating, we're not talking about how fast it's going, but how much it's accelerating. When it's accelerating, it's pushing against you like that, right? While it's accelerating, you feel a force on your back that's similar to the force that you feel on your bottom, right? The pilot is feeling two things. When you're in a car, you feel two things. You feel your bottom is in the seat, and your back is being pushed by the back. But usually, your weight is much more than the amount of push on your back. It's a relatively gentle push because cars can't accelerate that much, right? Like the example that we had before in the exam, I think it was 2 meters per second square or something was the maximum acceleration of the plane or something. But you can have a plane that has an acceleration of 9.8 meters per second square, in which case the acceleration of the plane is exactly the same as the acceleration of something dropping, which means that the feel of your back or on your back as the plane seat is pushing you will be the same exactly, not only qualitatively but quantitatively, as the push of your chair's bottom. So the bottom and the back will both be pushing with a force. This one due to gravity, this one due to the acceleration of the force. Pardon me? Well, yeah, you're in the chair. If you're strapped in the chair, you're moving along the wheels of the jet. The jet is firing, causing the jet to move. It's sliding along the runway on wheels, let's say. Because the jet is moving, the seat, which is bolted onto the floor of the jet, is moving. And if you're here, it's going to push you. If you're on the runway in front of the jet will also hit you and push you. Okay? But if you're in the seat, the back of the seat is pushing you. And gravity is pushing you up all the time. You're trying to fall down to the gravity, and the seat is pushing you up. Okay? And the back of the seat is pushing you forward. If the jet is accelerating with an acceleration of 9.8 meters per second square, then the feeling on you and the amount of force on your back is the same as the amount of force on your bottom. But here there's a force down and up, and therefore you're not accelerating in this direction. Okay, you have equal and opposite forces canceling each other, which is the purpose of the seat bottom. If the seat bottom wasn't there, you'd fall down. The purpose of the seat bottom is to provide that equal and opposite force to your gravity. Okay? Now how could it be that it provides the equal and opposite force to whoever sits in there no matter what their weight is? It's built in such a way that it could provide a maximum amount of force. If you push on it a certain amount, it'll push back that amount. If you push more, it'll push back more. Right? I'm pushing now on the table, pushing harder, harder. It's built to push back. The molecules are compressing in the table. It's like a spring. They're compressing a little bit when I push a little bit, compress more when I press more. There's more stress in the table than in my fingers the harder I push. But it's built to withstand that. And the floor is built to withstand the pressure of this and so on. Okay? So, when there's an equal amount of force pushing here and here, you have an acceleration here because there's no force pushing against you. Here you have no acceleration because the net force is zero. All right? When they're equal, so we measure the acceleration of a jet fighter, for example, in gravity sometimes. You say it's moving at 1g. In other words, the amount of acceleration of the jet is equal to the acceleration of anything being dropped down. Okay, so it's kind of like before we had a bullet being shot off with a constant speed and going down like this. Here we have a jet moving with the same acceleration as this. So basically, if you took that jet and an object and shot the jet forward and dropped the object, they'll cover the same distance in the same amount of time because they're both accelerating from zero with the same acceleration. Okay? So you can see that as kind of like a problem. You have a jet and it drops a bomb or something, right? And starting from zero. Obviously it's not going to be doing that, but let's say it's starting from zero, all right? And it's moving in that direction with 1g. This is moving in this direction with 1g, all right? If they were starting from zero speed, right, then the amount of distance that this would cover in a certain amount of time would be the same amount of distance as this would cover. So if I told you that the plane starts at zero, opens its bomb bay, drops its bomb, and accelerates forward with 1g, and we know it starts out from zero, so it'll go straight down, okay? If we know this distance, then we can say how far away is the plane when the bomb hits, then it'll be exactly this distance. Now this equality between the two leads us, if you think about it, to a deeper understanding of what mass is and what space and space-time are, and it led people, including Einstein specifically, to come up with the general theory of relativity, which is a geometrical picture of how mass energy curves space-time, and as a result of that curvature of space-time, objects in space-time have a tendency to move, to react in a certain way, and the resulting motion is what we call the motion due to gravity. In other words, the Earth goes around the sun. Really what's happening is the sun is warping space-time in its vicinity. As a result of that warping, the Earth moves along a certain trajectory because space-time is warped. And the trajectory that results is this. And we call that the motion as a result of gravity. But in general theory of relativity, there's no gravity, there's no gravitational force. There's space-time and there's matter energy. Space-time is warped. Objects always move along what's called the geodesic, like in some senses you can think of it as the shortest path. It's a very elegant formulation. And when you put that together, you find that it moves like this, and it simulates exactly what would happen if there were a gravitational force between